Good evening, madam. My name is D. Kullai Sharif. I am pursuing BTech second year in SRT in CSC B section. Today, my PPT presentation is about binomial coefficients. In binomial coefficients, it is given to prove that C0 plus C1 plus C4 plus and so on equals to C1 plus C3 plus C5 plus and so on equals to 2 power n minus 1. In this slide, we can see the introduction to the topic. The combinational identity we are exploring involves binomial coefficients. This identity relates sum of even indexed and odd indexed binomial coefficients. Our goal is to prove the both sums are equals to 2 power n minus 1. Moving forward to next slide, understanding binomial coefficients. Binomial coefficients denoted as Ck represented the number of ways to choose k elements from a given set of n elements. They can be calculated using the formula C n power k equals to fraction of n factorial k factorial n minus 1 factorial. The entire set of binomial coefficients can be represented in Pascal's triangle. Defining the even and odd sums. Let SC equals to C0 plus C2 plus C4 plus and so on represent the sum of even indexed coefficients. Let S0 equals to C1 plus C3 plus C5 plus and so on represent the sum of the odd indexed coefficients. We will show that both SC and S0 equals to 2 power n minus 1. In this slide, we can see the binomial theorem overview. The binomial theorem states that x plus y whole power n equals to sum of k equals to 0 power n Cn power k x power n minus 1 n minus k y power k. By substituting x equals to 1 and y equals to 1, we derive 2 power n equals to sum of k equals to 0 power n Cn power k. This represents the total number of subsets of an n element set. Moving forward to next slide, even and odd indexed sums derivation. By substituting x equals to 1 and y equals to minus 1, we find 1 plus minus 1 power n equals to 0 power n equals to 0. This gives us sum of k equals to 0 power n Cn power k minus 1 power k equals to 0. Hence, Sc minus S0 equals to 0 or Sc equals to S0. Relating sums to power of 2. Since Sc plus S0 equals to 2 power n, from the binomial theorem, we can express the total. With Sc equals to S0, we can substitute to find 2Se and 2 power n. By dividing both the two leads us to conclude Sc equals to S0 equals to 2 power n minus 1. In this slide, we can see the visualization of even and odd sums. The Venn diagram can effectively illustrate the partition of subsets into even and odd cardinal needs. Each subset can either have even or odd number of elements. This visual representation reinforces our understanding of how the sums relate to total subsets. Example with specific values. Consider n equals to 4. We calculate C0, C1, C2, C3, C4. The sum yields Sc equals to C0 plus C2 plus C4 equals to 1 plus 6 plus 1 equals to 8. And S0 plus C1 plus C3 equals to 4 plus 4 equals to 8. Both results match 2 power 4 minus 1 equals to 8. In this slide, we can see the induction proof strategy. To rigorously prove our identity, we can use mathematical induction. We start with a base case, proving it holds for n equals to 1. Next, we assume it holds for n equals to k and prove it for n equals to k plus 1. In this slide, we can see the base case verification. For n equals to 1, we have C0 equals to 1 and C1 equals to 1. Thus, C equals to 1 and C0 equals to 1, which equals to 2 power 1 minus 1 equals to 1. The base case is verified. In this slide, we can see the inductive step. Assume the identity holds for n equals to k, Sc equals to S0 equals to 2 power k minus 1. We will show it also holds n equals to k plus 1. We express Sc and S0 in terms of c power k plus 1. In this slide, we can see how to expand the sums. The terms for n equals to k plus 1 can be written as Sc plus S0 equals to C0 plus C1 plus and so on, c k plus 1. By the inductive hypothesis, we know Sc plus S0 equals to 2 power k. Thus, we know we need to evaluate how to c k plus 1 contributes. In this slide, we can see the conclusion of inductive proof. By adding c k plus 1 power 0 and c k plus 1 power 1 to the existing sums, we adjust the totals. This ultimately leads to Sc plus S0 equals to 2 power k plus 1 minus 1. Therefore, the inductive step is complete. Summary of findings. We have established the C0 plus C2 plus C4 plus and so on equals to C1 plus C3 plus C5 plus and so on. Both sums equal 2 power n minus 1, confirming the combinatorial identity. Our proof utilized both visual and algebraic methods for clarity. In this slide, we can see the future implications. This identity has implications in probability. Understanding these sums can aid in more complex problems involving subsets. Future research could explore analog identities in higher dimensional spaces. This structured presentation covers the proof of identity and explains the concept clearly and truly. Thank you, madam. Have a great day.